Now we are ready to introduce what's called the Riemann-Roch space with respect to given divisor F, given divisor A. More formally, it will be a set that contains functions such that A plus X is positive, or equivalently, the principal divisor X is bigger than or equal to minus A with respect to partial order we consider. Union of the zero of the base field K or the function field F. And we call such a space Riemann-Roch space. And that will be quite important from now on. Associate to the divisor A, or simply sometimes we say this is the A space of A. Later we will see that actually this is a vector space, but before explaining that, let me again consider an example in the rational function field. And let me consider the divisor 2p infinity. Here p infinity denotes the pole of X. And the corresponding A space contains functions whose principal divisors is bigger than or equal to minus 2p infinity, union 0. So here let me observe that what kind of functions lies in this space. For instance, we can see that the constant function 1x and x squared are elements, the A space of the 2p infinity, because the principal divisor of the constant one is 0, because the valuations of the constants are 0, and this is obviously bigger than 2 minus p infinity if you compare the coefficients of the p infinity. And similarly, x is an element in the x is a function in the A space of A, because its principal divisor, which contains its zeros and poles counting their multiplicities, is p0 and p infinity. This is obviously bigger than minus p infinity, because the coefficients of the p0 satisfies this inequality, and similarly the coefficients of the p infinity satisfies the inequality. And similarly for the x squared, it will be enough to observe that its principal divisor is the 2 times of the principal divisor of x. And with respect to partial order, we consider this, again, we can see that x squared also lies in L of A. On the other hand, we can see that neither inverse of x or x cubed or any power b which is bigger than or equal to 3 is not a function in the A space of A. For the x inverse, if we consider its principal divisor, it's going to be minus principal divisor, so that means p infinity minus p0. And in this case, even though the coefficient satisfies the inequality, the coefficients of the p infinity does not satisfy this inequality. So that means x inverse is not element in the A space of 2p infinity. And similarly for the x cube, if you consider its principal divisor, it's going to be 3 times the principal divisor of x. the coefficients of P infinity does not satisfy the inequality. To understand this definition 4, let me give some remarks. In the first remark, we can easily observe that for a function f being a function in the S-space of a divisor A means that for all places its valuation of the principal divisor will be bigger than or equal to minus valuation of VPA. And here also let me note that the valuation of the principal divisor X is nothing but the valuation of X at the P component, because we can write the principal divisor as VP of X, and we define the valuation of a divisor by checking its coefficients. So, and often we will use this characterization. So if we want to see that if X is a function in the S space, for all places, we need to check that its valuation at P is bigger than or equal to valuation of A for each P. And in the second remark, we will understand why it is called a space, because such a set forms a vector space structure over the base field K. And first, by the definition of the A space, we can see that the zero, it contains zero. So this is a non-empty set. By the definition. And if we consider a function in the A space of A, and if you consider non-zero constant C, since its valuation at every P will be equal to the valuation of X, because the valuations of the constants are zero. And since X is a function in the F space of A, by the definition of A space, we see that indeed this product also is a function in L of A. And to see that this vectors, this L of A, this set is also closed under the addition. Let me consider two functions X and Y. And if you consider the valuation at every P by strict triangle inequality, we can say that the valuation of its sum bounded below the minimum of their each valuations. And since X and Y in the A space, each one is bigger than or equal to minus P of A. And this shows us in that this set forms a vector space, K vector space. And if we write the divisor explicitly by regarding its positive and negative components, here Ni, Mj are positive integers. Actually, we can see that this vector space contains functions with pre-described poles and zeros that appears in this divisor with non-zero coefficients. What I want to say, if x is a function in the associated A space, by the definition, we know that its principal divisor is bigger than or equal to minus A. So this is mj qj minus ni times pi. And by the first remark, we can see that if we check the valuations at qj's, we see that the valuation of x each qj is bigger than or equal to mj, because it has valuation mj. And since this is strictly positive, we can conclude that x must have zeros at each qj of order at least mj. And similarly, by checking the valuations at these given pi's, so here, let me divide two cases, and Vp of x is bigger than or equal to minus ni. So in this case, we say that we will observe that x can have poles only at the places P1 up to PR of order at most ni. Because, I mean, for instance, if you choose ni equal to 1, that means Vpi for a fixed I, when I runs through from 1 to R. So if Vp of x is bigger than or equal to minus 1, so it can be equal to minus 1 or 0. So in the minus 1 case, so that means it can have a pole of order 1, or it has neither foreign pole. So this is why we say it can. And the upper bound for the pole orders can be observed that, I mean, if we suppose that if the function x has a pole at pi of order 2, in this case, minus 2 cannot be bigger than minus 1. So this is why the pole order should be at most ni. And thanks to this remark, actually, we can view the A spaces that contains functions with pre-described poles and zeros, roughly counting all their multiplicities. And again, as an example or the spatial case, for instance, in any function field, if we fix a positive integer n, and if you consider the divisor mp, we can check that this A space contains the functions which has only poles at p of order at most n. For instance, in the rational function lp to infinity contains functions that have poles at p infinity of order at most 2.